So Alice and Bob share this state. Alice gets row, measures the observables in that row. So Alice and Bob are sharing this state. When Alice gets the second row, she measures sigma z on the second qubit, sigma z on the first qubit, and she, I should say red if eigenvalue of -1, and green if eigenvalue of +1. So she measures sigma z on the first qubit, sigma z on the second qubit, and then if the first one was a -1 and the second one was a 1, she would mark this square red, this square green, and this square red. Now we know, because all three of these matrices multiply to I, that the observables must multiply to 1. So that means that there are 2 greens in Alice's rows, or even number of reds, because the reds were -1 and the product is 1. But Bob's columns all have, all multiply to -I, which means you get an odd number of reds in each column when Bob measures these. So Bob gets odd number of reds. And the last thing is that Alice and Bob are sharing the state. So Alice measures on her qubits. And I guess this would be AB, 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 AB. And Bob measures on his qubits. But when they measure the same observable, because this is in the 1/2, 0, 0 plus 1, 1 state, they get the same result. So when both of them measure sigma z, they get the same result. When both of them measure sigma x, they get the same result. Actually, when both of them measure sigma y, they get opposite results. But this is opposite, this is opposite, and we're taking the parity, so they get the same ±1 for this one, even though each of their qubits, they get opposite. So if Bob measured a +1 for the first qubit, and Alice measured a -1 for the second qubit, or rather, if Bob measured a +1 for both qubits, Alice would measure -1, -1 for both qubits. But then they are looking at the eigenvalue, +1 times +1 equals -1 times -1. And now, any questions? Yeah?
So under what circumstances do they lose that?
They never lose if they.
Oh, well, what's the 8 9s for then?
Oh, that's a classical strategy.
Oh, I see.
Classical strategy. Remember, the classical strategy, they had to agree on a square, and you cannot color all the squares so that every row has a even number of reds, and every column has an odd number of reds. And that's why they cannot win with probability more than 8/9. But a quantum strategy, because you have these observables, such that any product is identity here, and any product is minus the identity in the columns, means they can always win. Any other questions? OK. So the last thing I wanted to do was say what the simultaneous eigenvalues are in sigma x tensor sigma in this column. So sigma x tensor sigma x is equal to 1, 1, 1, 1. Sigma z tensor sigma z equals 1, minus 1, minus 1, 1. OK. And there are 4 eigenspaces. And first, if you know sigma x tensor sigma x, and you know the eigenvalue for sigma z tensor sigma z, you know the eigenvalue for sigma y tensor sigma y, because this times this is minus 1. So we don't need to worry about sigma y tensor sigma y. And the eigenvectors are 0, 0, plus 1, 1. So that's in the plus 1 eigenspace for this, and that's the plus 1 eigenspace for this. And that's plus, plus, and 1 over root 2, 0, 0, minus 1, 1. That's, well, that's still in the plus eigenspace for this, because 0, 0, and 1, 1, that's 0, 0, 1, 1, are both in the plus eigenspace. But this vector is just 1, 0, 0, minus 1. And you can see that it's taken to its negative by this matrix. So that's in the minus plus eigenspace. And then 1 over 2, 0, 0, minus, or 0, 1, minus 1, 0. And that's in the minus minus eigenspace. And 1 over root 2, 0, 1, plus 1, 0. And that's in the plus minus eigenspace. So that, if Alice measured this row and Bob measured, let's say, this row, so this is Alice, no, this is Bob, column 3. Alice, column, I want to do column 2. Eigen spaces are 0, 0, 0, 1, 1, 0, 1, 1. So if Alice and Bob shared this thing, Alice would, and Bob got, so Alice is measuring this row and Bob is measuring this row. Bob might see 0, 0, plus 1, 1, and Alice might see 1, 1. But they will agree on this eigen. And 0, 0, plus 1, 1 is in the plus 1 eigenspace of sigma z tensor sigma z, 1, 1 is in the +1 eigenspace of sigma z, tensor sigma z. So they will agree on which, they will agree on the color of this box.